All right, hello again. We are going to change gears a little bit today. So Monday we wrapped up that chi-square test of association. That was really like a wrap-up of stuff we had talked about before spring break, still looking at categorical variables and what types of conclusions we could make from an analysis using just categorical variables. Now we're going to move into looking at quantitative data a bit more, and specifically we're going to look at different types of models that we can use. And so this will really be the topic that we'll stick with for the rest of the semester is looking at modeling quantitative data. We'll start by just models with no predictors, which is the simplest type of possible model that we could look at. Then we'll start to look at adding one predictor and then eventually multiple predictors into our model. And so we don't really need to worry about that too much for now. That's just more of a big picture of where we are headed. And so there's a couple major goals of modeling in statistics. And so the first is just to use models for prediction. And so an example that we used earlier in the semester was exercise data. And so from our Stat 113 survey, we had recorded the amount of exercise students get per week. And so let's say we wanted to maybe use that data and then predict the amount of exercise that a student who wasn't in that data set actually gets. That's one use for these models. Another is we might be interested in inference about parameters in the model. And so remember, parameter, that was just a fancy word for like we did the population proportion. Now we're going to start talking more about the population mean. And so we might want to know something about, like, say, what is the mean amount of exercise students at St. Lawrence University get per week? And so the example that we're going to start working with is this GPA example that was collected by the Educational Testing Service. And so they collected data on 1,000 students, and the university that they collected from is unnamed, presumably to keep everything anonymous. And so they collected data on sex, verbal SAT score, math SAT score, and total SAT score, as well as high school GPA and first year GPA. So for now, we're going to ignore everything except for first year GPA at this school. And so the next couple of pages just show a brief preview of the data set, as well as a histogram. So remember, if we were just looking at a single quantitative variable, which we are here, one graph that we could make is a histogram. The other was a box plot. And so in this case, our variable of interest is first year GPA. And so we're going to think about writing out this model with no predictors as just some sort of like response variable. So we're going to call that y. And we're going to let that be equal to some mean plus some error. And so I'm going to label this as my GPA variable. And so this was first year GPA. And I'm going to say that that's equal to some mean that's common to everybody. So everybody has the same exact mean. Plus some error. And so each observation is going to have its own error. So just kind of rewriting this, in this particular case, we have first year GPA is going to be equal to the mean plus some error. And so sometimes we're going to abbreviate that error as this little epsilon, we're not going to worry about that too much for now. And so it's necessary to have this error in the model because people have different GPAs. If I didn't have that error, so I'm kind of blocking that out, then that says that everyone's GPA is equal to this common mean. But we know that that's not true. So all of you have different GPAs. It's not really realistic to just say that, okay, everyone has the same exact GPA of 3.2 or 3.1 or whatever the true mean is. And so we really have to have that error because GPA has variability. Simply meaning that not everyone has the same GPA. You could think about like a kind of silly model that wouldn't need an error term, and something I kind of came up with was if you were to model hours per day, some mean plus the error, well, the mean is just 24, and then you don't need the error because there's no variability in hours per day. It's always 24. So that's just kind of a silly example of something where you wouldn't need the error term, but in almost all real data, you would want this error in there. And so the biggest issue with this model kind of up here is that we don't actually know the mean. So we only have data on 1,000 students. We don't have data on every single student at this unnamed university. And so we need some way to estimate that mean. Using our data, let's not overthink it. If we want to estimate this unknown mean and we have GPAs from 1,000 students, what do you think we would use? So we would just use the sample mean. Which, just like we denoted the sample proportion as a P with a little hat on its head, ready to party, we're going to denote the sample mean as a mu with a little hat over its head. And so from the data set, that turns out to be 2.47. And so finally, we could write out what our fitted model is. And so to denote that it's fitted, again, I'm just going to put the little hat on top of this first year GPA. In our fitted model, we're just predicting first year GPA for all students that we don't really observe is 2.47. This model probably seems really silly to bother writing it out this way, but we're doing this so that we're set up for success in the future as we start to add predictors into our model. So the error term just kind of goes away in this fitted model just because our fitted model just represents the best guess for the response. In this case, first year GPA. So because of that, there's no need to include the error in the fitted model. All right, so that wraps up our introduction to modeling. In the next video, we're going to talk about using this really simple model for prediction, and then we're going to move into using the model to find something out about the population mean.